Hi there, my name is Tim Simpson. Happy to be joined today by my colleague Guha Manogharan to talk about Penn State's Additive Manufacturing and Design graduate program. A quick introduction to myself. I've been at Penn State over 20 years now. I'm in both mechanical engineering and industrial engineering, ME by degree, and I hold the Paul Morrow Professor of Engineering, Design, and Manufacturing. As part of that, I also oversee and direct the Additive Manufacturing and Design graduate program that we're going to talk about. And I'm also co-director on SIM3D, the Center for Innovative Material Processing through Direct Digital Deposition. This is one of the feature labs here at Penn State for additive manufacturing, particularly 3D metal printing. And it's a big reason why we have our graduate program and also the home or birthplace of Autodesk Netfabb's Ultimate, the simulation capability now available in Netfabb. We'll talk a little bit more about the origins of that and my colleague. But first, let's dive into the Additive Manufacturing and Design graduate program. So we got together probably 5 or 6 years ago now and started talking about this as our capabilities at Penn State grew. We started offering courses in multiple departments, and a group of us came together and combined those into a brand new graduate program that we've titled Additive Manufacturing and Design. I think the and design piece is key there and distinguishes us from other programs, in part because we emphasize that, design is really the key to differentiating yourself from one process to another. Anybody can buy a machine, load it with powder, filament, whatever, hit go. But if you don't really know how to design those parts for additive, then you're going to run into issues. You're not going to get the benefits that folks talk about and those sorts of things. So we were very intentional in that title. And for those of you, it is a master's degree, both MS and MEng, and we'll talk about the sort of details of the coursework and such in a minute. But first, at a high level, when we came together, we outlined these 3 program objectives. Certainly knowledge and creativity. Additive gives you all sorts of new freedoms because of the layer-wise fabrication of parts and components from different materials. And so we wanted to make sure that our students could apply, take the fundamental knowledge, critical thinking, problem-solving skills, and combine that with their creativity to come up with new uses, new applications for additive, and be able to defend those as part of that. Obviously, as a graduate program, and given the state of additive, there's a strong emphasis on research and innovation, right? Understand what's this current state of the art in processes, in design, in materials, the tools, those sorts of things. And how do you take those to then come up with innovative new solutions to then help drive the field as a whole forward. And then finally, being a graduate program and a relatively new domain or field of expertise, we also wanted to create thought leaders to go out and sort of become, grow themselves as leaders in the field, maintaining the highest ethical standards while learning how to apply additive to different, applications across different industries, overcoming design challenges as well. The program itself, shown here is one of our key figures or images. It was launched in 2017. I'll show you the statistics and growth here a little bit later on in this presentation. And we believe it was the world's first both online and resident. So we're doing a lot of hybrid education right now, given the state of the world and the pandemic. We've been doing this 3 years, co-teaching, students in resident, students online at companies, synchronous, asynchronous, mixing and matching, doing all sorts of things as part of that. And as I did mention, we have sort of 3 options. You can get a Master of Science. That's mainly for the resident students. Online students get a Master of Engineering. We're working to create a MS, Master of Science, for online students as well. We want to make sure that they have the right amount of research experience before we do that. And then finally, a certificate option. A lot of folks already have a master's degree. Actually, I think one of our students has like 4 master's degrees already, but saw the opportunities with additive and decided to pick up one more. And so if you don't, as I said, if you don't want to get the full program, you've already got a master's, you can pick 3 out of these 4 colored courses, the process, the science, design, and materials. I'll go into each one of those here in just a minute. And if you take 3 of those 4, then you get a certificate in additive manufacturing and design. So overall, it's 30 credits. The science of AM, design for AM, materials for AM, and AM processes. plus the lab. Those are core courses, 5 core courses, and each one is taught by a different department. So mechanical engineering, industrial engineering, we have a separate engineering science program, we have a separate engineering design program, and then of course material science and engineering. And so I think that's, it is a truly multidisciplinary program. And I often joke, my job as director is I get to keep at least 5 department heads, 2 associate deans, 2 deans, and World Campus, our online administration, all happy at once. So I fully appreciate, what aligning a program with a department, that's great. But with Additive right now, you got to be, work across disciplines, multi-interdisciplinary, those sorts of things. And I'm willing to deal with that headache, and I think it's to the benefit of everybody involved. And we've seen, based on the growth, I think it's been successful as well. We do have in the middle there, the hands-on metals lab. Come into the lab. Guha is going to talk about that in a bit more here after he introduces himself. And that can be done on site. And so while everything else is online, you do have the option of coming on site and using our facilities in Sim3D, along with other capabilities. Alternatively, though, if you have access to, the metal 3D printers, mechanical testing, microstructure characterization tools at your company, then you're welcome to do that there. And we sort of send you Guha sends you the lab notebook. You follow along in parallel and submit your assignments. So we've done that with a couple of folks now. Imperial Machine and Tool was one of the first. Joe Sinclair there, one of our first graduates. But we've talked to others as well as we've ramped up exposure. And particularly now, with limitations on travel, we could not bring folks to campus this past summer. And so we've been much more flexible, trying to work and accommodate students' needs online, the online students' needs, with the resources that they have available at the company. So let me talk briefly about, just a slide each on our courses. For those of you that are interested in this, obviously the first course everybody gets is that survey course. And I'd say majority of schools out there now that teach and talk additive have something like this. You learn about all 7 processes based on, ASTM standards there. The fundamentals, materials, polymers, metals, ceramics, concrete, bio, it's at a high level, right? It's a survey course here. We do get into the digital workflow and talk about the software tools and methods that are out there. A key piece of that is then reverse engineering, 3D scanning, even doing introduction to CT and the role that plays these days. I like the image here. We've been doing some work with Vortic Watch. Actually, RT Custer was an alum of ours. Spun out technology. We helped them design and connect with a manufacturer, again, Imperial Machine and Tool, that now produces 3D prints, titanium watch cases for custom watches that they make. Meanwhile, I've been getting that watch case printed with all these different processes and then CT scanning them here. And so you can now see this is a great way to compare and contrast sort of what's the inside of an FDM part versus, Mark Forge versus electron beam, EBM, DMLS, direct metal laser sintering, or laser powder bed fusion, as we're more used to calling that now. I've got almost all the processes here as part of it, but it's a great way to see both, externally what the parts look like, dimensional integrity, but also on the insides there, because that then ties into, the economics, the limitations, when can and can't you use this, and then how do you select the appropriate technology there as part of that. So, course is usually taught by my colleague Sanjay Joshi in industrial engineering. He's been teaching some version of this course for well over 20 years now since the technology was invented. So great survey course and a great sort of foundation for everybody. I think the other foundational course is what we call the science of AM. And so this is taught by Ted Reutzel and Abdallah Nasser. They're colleagues of mine in the Applied Research Lab. I work closely with them through Sim3D, but they're also affiliated with our Engineering, Science, and Mechanics department. Here they go really into, the physics and science of what's going on when the laser hits the powder and spatter comes up and all these sorts of things. How does that vary? How do you model it? How do you simulate it? How do you analyze it? Of all the courses we offer, this is by far the most equation-based, the most challenging. These guys are really getting into the nitty-gritty details there as part of that. And so we do want to make sure when we're admitting folks to the program, being able to, a lot of folks sort of have to, if you've been out in industry for a while, you got to refresh or remember what all these symbols and equations mean. But I think at the end of this, students, the feedback I get is, yeah, it's tough, but I really now have a much better sense of what the heck is actually going on, in a laser powder bed fusion or in a powder feed directed energy deposition process as the powder laser hits and evaporation, those sorts of things, when and how do defects occur, how to sense different physical phenomenon as they're going on in the powder bed, for instance. This is really sort of the core of this course. And so between, these are both the processes and the science course are usually taught together in the fall semester, so they give you a really good foundation going forward. The third class then, this is taught by Allison Beasy, a professor in material science and engineering, and it's really the additive manufacturing materials, right? What happens with the process, structure, property relationships. This is one of Allison's figures that she uses in the class there, and says, hey, as we're doing, and this part's made with directed energy deposition, so high power versus low power, different scan speeds, travel speeds there. What does that do to the heating, cooling? What does that do to the microstructure? Based on the microstructure, what does it do to the properties there? And so again, this is now building off of the science that they've learned in the other courses and saying, okay, let's take that down to to the processing level, to the microstructure. How does it evolve? How do these solidification, solid state transformations occur in different materials? How and where do defects occur? Really understanding now not only when they might occur, but what is the impact of those defects, right? So why do pores not full density? How do residual stresses build up, and what does that impact going on? And then of course, how do you post-process, heat treat, the mechanics of structures, etc., characterization techniques. Obviously, primary emphasis here is on metals, but she does as well talk about polymers, ceramics and other materials. So again, a good, real deep dive by a material scientist into the material science behind additive manufacturing. And then Nick Meisel, faculty member in our engineering design program at Penn State. He teaches the design for AM course, and many times, schools will have other schools or universities will have the process course, and then the design piece or even the materials piece will sort of be a quick couple lectures on that or something, or maybe there's a separate hands-on project. We've got a whole class now dedicated to just design tools, design methods, software, the research that's going on in these spaces. And Nick has everybody do sort of not only a hands-on project, but also a deep dive into the literature and the design research. How we actually have some studies going on how do we teach design for additive manufacturing? How do we use that and encourage creativity as we're learning about both the restrictive, and the opportunistic aspects of design for additive manufacturing in the various processes. So again, building off of the process knowledge you learned and the fundamental and material knowledge, now how do we use that for design to enable mass customization, topology optimization, multi-materials, functionally graded materials, consolidated multifunctional designs. How are you dealing with CAD files throughout this? Biomimetic, bionic, designs inspired by nature, and a couple of examples here of some of the tools that, some of the projects, that students work on. We've had some nice interactions, both, Fusion 360 Autodesk, Netfabb, and topology, some of the top op tools that are out there, Inspire and OptiStruct, really trying to get them some hands-on opportunities with all of this. And so then, you've got these sort of four core courses. The fifth one then is really bringing that all together. It's sort of this capstone experience, although we don't technically call it that. But it's, it's the Metals AM Lab. It's the hands-on component of the program where you're building and breaking parts as part of that. And so Guha is going to talk more detail about this, and in particular the simulation analysis tools and capabilities that we use here. in that course, learning, Netfabb for both build prep and planning and process simulation, for example, really gives then, insight into the economic drivers, the challenges not only with printing, but then, post-processing, right? And so how do you, design, datums, reference points, fixtures into parts so that then you can machine them afterwards? How do you use, additional post-processing techniques, abrasive flow machining, chemical etching to get, good surface finish, etc. When and where do you use analysis tools on this, not only for the design, but again, process simulation and later on. Students then develop, they get a little a test problem as part of that project that they go through start to finish. So they go through the whole workflow, they do the simulation, they do the analysis, they develop a build plan, estimate cost, time, define, post-processing needs. They also do, non-destructive and destructive testing. Guha will talk a little bit about the CT, computer tomography, scanning that they do in there, among others. And here's one example. I think this was 2 semesters ago now. It was a little small piston engines there that you can see the original one up top, 55 parts, about 141 cubic centimeters of volume. A team of 2 students redesigned it. The goal wasn't necessarily part consolidation, but they did get from 55 down to 43, but huge reduction through lattice structures and some optimization there to get down to 40 cubic centimeters of printed material that then of course reduces build time, reduces material, reduces cost, etc. And the students in the course were pretty excited that once it was assembled, it all fit together, and then it actually worked. So Guha is going to show some videos of that a little bit later here. So where does this all take place? Well, as I mentioned, Sim3D is at Penn State. We're out at Innovation Park there. We've got about 8,000, actually 10,000 square feet now and expanding. Sim3D has been up and operational almost 8 years now, sort of initially conceived about a decade ago, and then proposals, and by the time you get everything together and moved, etc., we've been up and running for quite a while. We were very fortunate that the space became available, funding, sort of the right people all met. I say that many stars aligned to enable both Sim3D and of course now our additive program. And they all came together, right at this, this uptick of interest in metals and additive manufacturing. So initial funding actually came from DARPA through their open manufacturing program. We served as a demonstration facility for additive for DoD. That meant we had roughly about 1,000 visitors a year that would come through and ask questions and things. We'd run some technical exchanges, bring people in to talk about materials and processes and those sorts of things. And as we did that, we built out this research infrastructure across the university where, in Sim3D and elsewhere, how are we collectively advancing the technology for additive? We do R&D, we do development work as part of that, right? And we're really focusing on, engineered components and structures. It's not just, trinkets and bobbleheads anymore, but really components like this V22 link. My colleague Ted Voitzel and Wes Mitchell and the team helped the Navy. This was the first flight critical component that they flew on their V22 Osprey helicopter. So we actually did a lot of the initial design and development and validation work in Sim3D. I joke it's probably the most stressful 15, 18 months of Ted's life, but nonetheless, we are now able to, we've got that feather in our cap and continue to expand on that. I think another unique aspect is our role of sort of being as an honest broker for companies, providing guidance, technical assistance, tours, come see this, come see that, to really then help demonstrate, validate the technology. So we get a lot of companies that come through and say, I heard this, I heard that, this software, that hardware vendor told me this or that. And I joke, we give them the good, bad, and ugly as part of that, because, end of the day, we're not trying to sell machines or equipment or software. We're just trying to help train and educate the next generation of students out there. And of course, certainly opportunities to train and educate the existing workforce and develop the talents out there, because it's amazing just how much this has taken off. And even employees that have been just working 3, 4, 5 years have completely missed all of the educational opportunities there. And so that's part of why, again, we launched the online version in addition to the resident one, so that students, industry practitioners can take the program and enroll as part of that. We are fortunate in Sim3D to have a variety of metal additive manufacturing systems. We are now up to, we have 4 laser powder bed fusion systems. We're actually in the process of getting a 5th. We have a close partnership with 3D Systems. We've had several programs together, so they actually have 2 employees that are stationed in one of the offices there and work closely with us on programs. So we've got the Pro X200 initially and the 320. We're getting yet a new system for them for several programs we have with America Makes, GE, and several others that are building out and growing. We have an EOS M280. That was our first initial purchase. And then the little small system there is from Exact Metal, actually a startup coming out of Penn State from a student intern who said, why the heck are these machines so expensive? And now he has a small, it's a 5x5x5 laser powder bed system that sells for about $100K. They've launched, they're across the street and have almost, I think, 15 employees now that are doing their best to survive the pandemic and get machines out there. We've got 3 directed energy deposition, or DED systems that have powder. The home-built system, as you can see with the glove box in the middle. Optimex MR7, this has been here 10, 12 years now. And then, of course, the DMG Morrow, we were fortunate a couple years ago to be able to acquire one of these. It's a hybrid system, so it is laser with powder and then a full 5-axis CNC capability as well. It is a beast and an impressive machine. And then about 2 years ago now, we did a custom-built DED laser wire feed system that has both hot and cold wire feed capability. The robot there that you see has roughly about a 10-foot wingspan on it for reach, so we can make some pretty big parts, as you might guess. This was sort of leveraging knowledge we had previously. We had a Sayaki system, which was an electron beam wire feed. We had that system on consignment for the first 3, 4 years that Sim3D was open, and so we've continued to be fortunate to have a nice range of capabilities. I think the other aspect that makes us unique is that by working Penn State with the Applied Research Lab, I sort of call Sim3D sort of a joint venture. We're not a separate company, we're part of the university, but nonetheless, we can do research and translate that into commercial and other solutions that are out there. And so many of the times we're working with companies on doing that as part of it. And so, we've got well over 120 faculty, staff, researchers, students, postdocs that are involved across, I think if you count it up, at least 15 different departments. And some of those are, folks specializing in design for additive materials, polymer materials for additive, et cetera, to others that are sort of tangential. We sort of think of it as a matrix, a vertical, for instance, within gas turbines or heat exchangers or medical, where folks are not specific additive experts, but we work with them to understand, what and what not to do for additive in this domain or that domain. ARL, the Applied Research Lab, not the Army Research Lab. It's a university-affiliated research center with Penn State at UARC, celebrating actually its 75th year now, and is really the director there and leader on Sim3D. And together, as you see in the figure, this is sort of really working, from basic to research to implementation. As I said, we can span sort of all TRLs as part of that. ARLs, sweet spots in the middle. Penn State faculty, sweet spots in the research, and then working with companies directly, help implement them, transition that technology, or with, like the Navy, for instance, actually working with them to transition knowledge on this V22 link that then is now printed, and flown and implemented by the Navy itself. So some great opportunities there that, as a faculty member, also gives me great insight into what are the real challenges out there, both at the implementation level, at the development level, and even all the way down, what's the basic fundamental research. So some great opportunities that have come in the past, 7, 8 years now as part of this. And I think one of the more exciting ones that you're, familiar with, I think, and part of the reason we're here talking today is because of my colleague, Pan Michelaris. So he and his students, customized some finite element analysis code that he was doing a lot of work in welding research and applications, modeling and thermomechanical modeling and simulation. He was able to take those tools, adapt them first for DED. You can actually see one of the very early experiments here, just doing some deposition with a bunch of thermocouples that he's now using to help validate his predictions and his distortion models. He then figured out how to scale that both down for powder bed and up to a full part, and was really one of the first, if not the first, to be able to model and simulate an entire part as it was being built with laser powder bed fusion. That was then demonstrated for even large scale components. I still remember there was a wing that a spar that Sayaki had made, 12 feet long, that he modeled and simulated and demonstrated how to use that to then mitigate distortion. A lot of success and interest, so he spun out a company, and then 3 or 4 years later, voila, as they say, the rest is history. Acquired by Autodesk on March 4th. And now everyone has access to the tools and capabilities that he and his team developed. He's left Penn State, but he's across the street still in our innovation center there. He and his 5 or 6 PhD students have been enjoying themselves. So at this point, I want to hand over. We talked about the capabilities in Sim3D and simulation and modeling. I want to hand it over to my colleague Guha Manogharan to introduce himself, and then spend some time on specifics on what he's doing in his lab to perhaps give you some new ideas, things to think about as you are trying to implement either simulation and modeling tools within your courses or at university, or trying to implement your own metal hands-on lab as part of that. So with that, Guha, please take it away.
Thanks, Tim, for your kind introduction, and thanks to Autodesk for having us over to come and talk about our additive manufacturing and design program. I'm really excited to talk about specifically this Metal AM lab course that we have, which is required as part of the AMD program. So just a brief introduction about myself. I've been at Penn State for going on 5th year now. So I joined Penn State in 2016. So my lab is the Systems for Hybrid Additive Process Engineering Lab, the SHAPE lab. So we primarily focus on experimental manufacturing research in additive and hybrid post-processing, with an emphasis on the design requirements for not just the AM, but also the post-processing and eventually the final application. And in addition to the direct metal AM work, we also work on 3D sand printing, and also on post-processing specific to abrasive flow machining and batch finishing. In addition, our application domain has been primarily aerospace and biomedical, with a specific emphasis on patient-specific implants that we do in collaboration with orthopedic surgeons and clinicians from our collaborative institutions. So with that said, in today's talk, I'm going to specifically focus only on the Metal AM lab course, which I'm really excited to talk about. So when we started putting together this program, this new the new AMD program, as you might have already observed from Dr. Simpson's presentation, so we have theory courses that talk about the laser powder interactions. We also have survey courses that gives an introduction to the workflow and some amount of cost economics analysis. And we also have courses that are specifically focused on design for AM and so forth. So this Metal AM lab course is designed in such a way that you take all the other courses, the theory courses, before you take the AM lab course, because in this course we have only 2 lectures. One is the safety at the very beginning of the course, and 2 is what is the overall course objective, mini projects, final projects, and overall structure. Other than that, students are in the lab or in the testing facility or in other kinds of facilities which I'll talk about, instead of being inside the classroom, because we wanted this to be particularly a very hands-on AM lab course where we take an idea of a project which is which is what we always work towards at the end of the course, where it has to be a functional part, which means we have to take into account the distortion, support structures, tolerancing, and post-processing. And there has to be multiple parts that have to be assembled together, and there have to be some kind of functional applications, whether it is thermal applications or whether it is mechanical applications. So the objective is, at the end of this course, students understand and apply the entire workflow, starting from reverse engineering of an existing, for example, a miniature engine or a heat exchanger, and use appropriate design for AM tools to redesign, to perform analysis and simulation, including the Autodesk software suite that I'm going to talk about, and then develop build process plan, evaluate distortion, predict what will be the machining elements that is required, and finally perform a non-destructive inspection and some destructive inspection of test coupons. And one thing I would like to point out here is this course is offered to both resident and the world campus students. So the resident students take it during the entire course of a semester, typically a spring semester, whereas the world campus students, as you can see a picture from a year ago, they come to campus for 1 week from Monday through Friday, 8 to 5, 40 hours of contact for the 3-credit lab course, and we pre-package what material for the students before they come to the campus. And we have also developed a virtual desktop where all the software related lab sessions are done prior to coming to campus. And when they are in the campus, they have a workflow that is established through the workbook. They have a mini project that they have to complete before the end of the middle of the week, and then they have one final project that they have to complete at the end of the week, which they finally go back to their employers or go back to their workplace, and then they finish their report and then they submit it. So it's a very intense 1 week, but the feedback from the students have been fantastic. So they are able to see in action the in-process monitoring that they have learned in the engineering science course, and they are able to perform mechanical testing on AM parts of different build conditions, which they have learned in Dr. VC's course. They are able to apply lightweighting and other design for AM concepts in their final project and their mini project as well. So I'm going to give a quick snapshot of how we have organized this particular course. We've offered this three years now, so going 3 times now, and going into the 4th year. So again, I would like to emphasize is the focus is on culminating hands-on experience. And speaking from my personal experience, when I got into Metal AM 14 years ago, I was focused primarily on developing materials. At that time, we did not have the software simulation capabilities that we have now. And also speaking with my peers who worked along with me, so the lessons that I have learned, I would like to pass on is, Metal AM is just not the process itself. We need to understand how the powder flow and the powder interaction and the oxygen pickup in the powder will influence your build conditions. How your build conditions will influence your defects, how they will influence your final part properties, how your design and your build orientation will affect build failure and distortion, how your support structures could affect distortion, and how to design for post-processing in all of this at the end of the day. Because I always say that your printed Metal AM part that comes out of this course project should not be that just sitting on a desk to show that we printed it. It has to have a moving component. It has to have GD&T associated with it. So that's kind of our motto when we come to this particular course, because I think at the end of the day, when our students graduate, regardless of which section of the value chain that they are in, if they are from the materials group, or if they are from the designs group, or if they are from the processing group, or if they are from the end user group, so they all have a holistic understanding in both breadth and the depth that is required to master Metal AM process. So here is one good example that Dr. Tim Simpson already showed to you, where we reduced the amount of parts that is required for a hot air engine from 55 to 43, about 22%, and more impressively reduced the weight to 71%. And here is a quick demo of the engine running. So as you can As you can see from the video, the key requirement that I have for these projects are the engine has to be working on whichever assembly that we have is working, and it matches or exceeds the original functional performance, in this case the RPM. And here is another example, and this is a fairly complex layout of the original design, but we reduced almost 46% of the amount of parts, and also reduced 43% or close to 44% of the amount of material. And specifically with respect to these examples, I definitely want to credit the students in this course, and also those who did this particular two projects on taking on the challenge of reducing the amount of weight, reducing the amount of parts that is required, and still achieving the same functional performance. So the rationale behind this approach is, if you are able to do this as a functional example as part of this course, then they will be trained when they go to work for an aerospace company or to go work for a defense vendor, that they are able to understand what are the functional requirements, what are the design opportunities that we have, and what are the considerations that they need to take into account throughout the process of AM workflow. Speaking of process simulation as part of the course, here are two good examples of using our Autodesk AM software suite in predicting what is the amount of distortion that we can have for a given material, for a given laser conditions, and what will be the likelihood of displacement within a particular magnitude if you're using different support strategies. And these were all simulated using our Autodesk software suite. And the other aspect that we use, and you will see in slides that are to come, is we also use this to simulate different laser scanning strategies, which will be then used to understand the process structure property correlation. So for example, here is the first of several round-robin lab sessions that the students experience. As you can see, we have pre-prepared samples in order for the students to go into, for example, in this case, do non-destructive testing using X-ray computer tomography, where we have prepared samples with different laser power, speed, different beam focus offset strategies, and so forth. And students are now able to understand the AM processing conditions with their simulations, with what they can visualize from X-ray CT scan. So they're able to quantify what is the percentage of defects, what is the difference between a keyhole defects, and what is the difference between a lack of fusion defects. And in some cases, for example, in this biomedical application of the proximal humerus fracture head, they're also able to use surface deviation analysis features that can also be done using X-ray CT that cannot be otherwise quantified, to look at what is the deviation of all of these lattice structures. And as I said, we prepare all of the samples for students to understand the process structure property defects. So for example, in this case, purposefully designed samples where the layer offset, the edge overlap offset was not perfectly selected, particularly to leave contour defects, and then the students can go ahead and understand how to quantify it from CT, how to observe it from SEM, and then when they go on to do mechanical testing, understand if there is any effects of these kinds of internal defects as well as surface defects that we produce. And also we have started introducing rapid qualification of AM parts. So instead of always doing dog bone testing, can we do quick and relatively faster and easier micro hardness and nano hardness testing, and see what is the correlation between AM processing condition, AM material structure after printing, and what is the micro hardness and nano hardness, and then what is the bulk testing. So try to establish both the micro and the macro mechanical properties. Speaking of macro mechanical properties, we have a very excellent facility in material characterization lab, which is part of the Material Research Institute at Penn State. So we have all the characterization capabilities that we could need for not just characterizing the part and its mechanical properties, but also the powder and its biomechanical performance and biochemical response as well. So in this particular lab, so far we have introduced digital image correlation, which will be useful for the students, not just for the mental AM, but also beyond, in understanding how to use image-based plastic strain fields and correlate that back again, as I said, to AM processing conditions that we have purposefully prepared different samples at. And in the last iterations of this course, which was this past spring 2020, we have also significantly increased the amount of post-processing that the students do for their parts. So we purposefully selected two groups of parts, one which require external surface finishing, for example, gears, and one which requires internal surface finishing, for example, heat exchangers and heat sink. So I'll first talk about the external surface finish. I would also like to note that we also have EDM resources in-house that really helps us when it comes to turning the parts around very quickly in terms of going from printing, stress relieving, getting the parts off the plate, and performing machining. And we are at Penn State, we also have two different types of surface finishing capabilities that now the students are trying to understand what is the effects of the build orientation, surface roughness as AM, and given an RPM and given the amount of time and a particular abrasive media, on what is its effects on reducing the peak surface roughness on external surfaces. So we have both the vibratory ball machine as well as the centrifugal disc machine from Walter Throb. And this was a post-processing process that we used for the first time in the course this past spring. I was very excited about this because we were learning about this process as we go along. It's the abrasive flow machining. We have an extrude system. So very simply put, we have abrasive media in a mineral oil or a similar medium with varying viscosity that we can choose, and we basically pump the material through the surface. We have used it only for internal channels, but there are other examples that you will see that people have also used it for external channels. So we just first used this for this particular spring semester. We are really excited with the preliminary data that we have gotten, and the students were learned not just the AM, but now they are also thinking about how to orient the part. For example, if they're printing a manifold or they're printing an heat exchanger, how to orient the part and what should be the wall thickness that they should design for, not just for successfully being able to print it, but also for successfully performing surface finishing. Here are some good examples of where abrasive flow machining have been used in both internal surfaces as well as external surfaces of printed AM parts that we were able to find. And this is a very quick snapshot of what we did with respect to surface finishing. So we also looked at what is the effects of different bend angles and different bend radius. We found very interesting results when it comes to how thin of a wall can we print and be also be able to successfully perform abrasive flow machining. So the biggest takeaway for us from this particular post-processing was the surface roughness was significantly reduced, but most importantly, what I thought was a takeaway was the variance in the surface roughness from a part all along the build and across the build as well. The variance in the surface roughness has significantly reduced. So these are really quick snapshots of what we have done with the Metal AM lab course as an entire processing workflow. And I'll be happy to answer additional questions that you might have during the question and answer session. And thanks, everyone. I'll hold on the line and I'll let Tim wrap the presentation up.
So thanks, Guha, for that great overview on your metals lab course, ME 566. I do want to mention to everyone that we actually keep all of our course syllabi, number of credits, when's it offered online. Give you the link here at the bottom of this PowerPoint slide to go in and click on any of these and take a look. Again, these first 5 are our core courses, along with Guha's course there. And then other ones, electives that we're slowly developing. We've got courses on bioprinting, advanced materials for aerospace, legal issues. I'll talk on that more in a minute. Feedstocks, polymer materials, and composites. And so we give you the depth across multiple, and then you can really deep dive and drill into some of these other aspects as well. We're also very flexible. If you've been enrolled in another program or have some more credits you haven't used yet, counting those towards electives. In particular, several companies that we've worked with, students have been taking courses toward a degree here and there, we will work with you to count those as electives, and then voila, you've got, you know, almost a third of the credits done right off the bat, and then get into the details and do a project with that. I did forget to mention that earlier. You know, as you know, a wrap up after the coursework, students online do a paper. So they work with an individual faculty member on a project of interest to them. Papers do not have to be made public per the graduate school, like a thesis or dissertation. So great opportunity there for companies to work on something that is, you know, perhaps confidential, you know, will help them along in their job and those sorts of things. And then the resident students do a thesis, which could be a short paper or a full thesis, depending on how they set that up with their advisor. And we've seen some great projects along the way there. Reminds me, as I see this slide, I forgot to point this out earlier, but this particular one, all sorts of failures going on. This was the first half of a piston crown. You may, if you've perused the Netfabb Ultimate, you know, and simulation capabilities, you may have seen this. This was by far one of my biggest failures, multiple failures to date. You know, I think it was 8 times before we got this right. From you know, the mess that you see there, excuse me, recoder blade issues to cracking that both happened during, you can see right down here, during and before, sorry, during and after, and even to you know, small support structures in there that failed trying to provide some reinforcement. So turned out after the fact, you know, we shared the geometry with Penn and his colleagues, and they simulated and said, you're going to have an issue right here. And lo and behold, we had an issue right there. And I said, I wish we had done that, you know, 6 failures ago. But nonetheless, the tools are out there now. And if you're not using them, I strongly advise you to take advantage of those. Speaking of other electives, I mentioned briefly our new legal issues of additive. This was a combination of business law and additive manufacturing. My colleague Dan Cahoy at Penn State, and then we've actually hired as a temporary instructor, actually an affiliate instructor now, Chris Higgins from Oric. He actually headed up co-founded the 3D printing legal group there. And the two of them combined, and in the summers, offer this course, which I think is unique and one of its kind. You know, they have students understand, you know, how do you create contracts, use, you know, IP secrecy agreements to protect your ideas and innovations, particularly in the 3D printing and trade space. Liability law, who gets sued if something fails. Creating trademarks, you know, how do you protect a CAD file? Can you protect a CAD file versus a part? Can you use copyrights, design patents for your, you know, additive designs and creative designs? And then, you know, cybersecurity obviously is an issue as well. If somebody can hack your file or hack your printer, how do you protect that, ensure privacy, et cetera? So this has been a great offering. And interestingly, Chris Higgins, you know, he's a partner at Oric, so he's actually practicing law and has been involved with several high-profile cases lately between some of the 3D printing companies out there. And so he does, obviously, he cannot talk about, you know, the details or specifics of the case, but, you know, he can certainly, based on what's in the news, you know, they've actually created a couple of their homework assignments, you know, in real time as things unfolded there, saying, hey, based on what you've learned, you know, what would you do in this situation? And so then Dan can, as the faculty member, talk about the, you know, from you know, what the theory says and practices are. And then, you know, Chris says, well, actually, no, you know, here's really what goes on, or vice versa. So it's a great dialogue there that they learn from each other, and certainly the students learn from each other. And I think this is probably the first time that an engineer ever really has to stop and think about when and how do I interact with my legal department as it relates to, you know, in this case, additive. So a lot of positive feedback. The other cool course elective that we did last fall, and we'll be doing it again here, is our 3D printing concrete, or AM construction course. This is actually done collaboratively with arts and architecture, landscape architecture, architecture, engineering design. We had a team that was competing in the Mars Habitat Challenge a couple years ago, came in second place. And so now they've taken their knowledge and distilled that into a course that's lectures plus a hands-on lab. You can see here a picture of some of what they were doing in there. Great opportunity for students to get exposed to a new area of additive that's really taken off right now. And I know as well, there's some interest from Autodesk and others, as you're not only programming the robot, how are you also programming, this structure, that structure, given the, given the market penetration of Autodesk tools in the architecture industry. I think this is a very, ripe area for future research and growth and opportunity. And so I'd say stay tuned to this if you're not aware of it. So finally, how's the program doing? Well, here's sort of the numbers. We pulled these together as of where we are now. We're over 101 students enrolled, the dark blue bar there. As part of that, you can sort of see the growth from launch to the current day. We've got more than 60 unique companies enrolled. It's been interesting. Certainly the early adopters were, the usual suspects that you see talking about additive. But now we're getting, smaller companies, different industries, et cetera, that are starting to take the courses and learn about additive. And we're slowly getting our graduate students out there. We're up to 23 graduates now between the master's and certificate program online and resident. And so it takes, what we're seeing is roughly, 3 years, 2.5 to 3 years, give or take, for a student working in industry to take all the courses and complete that, one course a semester. Obviously, you can do it faster or do it slower depending on things, and we have been very accommodating, particularly now with all the disruptions and everything going on with the pandemic, to adjust schedules, defer grades, realign, labs and deadlines, et cetera, as part of that. So we recognize, industry, students online in industry certainly have a lot more demands and challenges on their time compared to, students that are here in resident. So we are flexible in that regard, and I think I've been very pleased with the growth of the program to date. And so with that, I would like to thank you for your interest. I hope you've enjoyed our presentation today. Feel free to reach myself at the email or Guha. Email address is provided there, and of course we're active on social media. And follow me at PSU MakerProf on Twitter, and of course we post a lot on LinkedIn. We've got a group of additive manufacturing and design group that we coordinate there as well. And finally, certainly the presentation examples of things would not be possible without all of the efforts of the faculty, students, staff, and ARL and whatnot. This image in particular, I love it. One of our engineers, Corey Dickman, who is one of the operators and designers, managed to, with some finagling of the shutter settings and speeds, capture this for one of our builds. It reminds me a lot of Tron, like a Tron disc, if you're familiar with that from several years ago. So super hi-fi. But again, love it. It's an exciting area. I hope it's interest to you as well, and happy to chat more if you'd like to reach out. Thank you very much.